Alright guys, in today's video, I'll be explaining how a derivative works. So first, let's start off with the definition of a derivative. So a derivative is just the instantaneous rate of change at a given point. Of change at a given point. So basically this just means the slope at a point. So let's just say we have the graph of a function. Let's say our function is this, for example. Let's say we want to find the slope at this point. Let's call this point A. So x equals A. Now, this is pretty tough to do accurately, graphically. So let's just use a secant line, for example. So let's pick another point on the graph. Let's pick x equals B. This is just some arbitrary point. We draw a secant line, so it would be like this. Now, this seems like it's really close to the slope of the line. And as you may know from geometry, the formula for a secant line is f of b minus f of a over b minus a. What does this look like? You guessed it, it's the slope formula. Now, we want this to be as exact as possible. This is just an estimation. But what if we brought x equals b even closer? Let's say we picked another point, x equals c. We picked x equals c to be here. Second line would be similar to this. Now this is looking very close to a tangent line. And as we know, a tangent line gives the instantaneous rate of change at a given point. It gives the slope at that point. This is getting very close. Now, we could say, all right, let's just do f of c minus f of a over c minus a, right? That equals the slope. Now you might be thinking, well, what if we just pick the same point to be here? Let's just pick another point right here, exactly at where a is. So x equals a again. Now, here's where we run into a problem. We can't pick the exact same point because it would result in a value that is indeterminate. The denominator would be 0, so that wouldn't give us a definitive slope. So, but what we can do is we can set up a limit. So let's say the distance between an arbitrary point very close to x equals a, say here, and the distance between them is h. Now what we can do is we can say limit of h approaching 0, that's distance between that point, that brown point, and a, and because h can't be 0, right, since it would be indeterminate, it would give us an indefinitive answer, the slope. So we want to pick something very close to it. Now this gives us the instantaneous rate of change at that given point of the function generally. If we want it to be at that given point, we would do f of a plus h minus f of a. That would give us f prime of a, otherwise known as d over dx, the derivative of f of x given at a. Now what if we wanted to find the slope of the function just generally? That's easy. What we do is we do f of x plus h minus f of x over h. And that gives us f prime of x, otherwise known as the derivative of f of x. Let's do an example. So let's say we want to find the derivative of x squared, right? Our function is x squared. So what we first do is we do limit of h approaching 0. And what we want to do is we want to do x plus h squared starting off, because our function is f of x, right? And here's f of x plus h. So we put x plus h squared. We put the x plus h in replacement of f of x. So it'd be f of x plus h equals x plus h and then squared. That's why we do x plus h squared. Then we subtract f of x from that. F of x is just x squared. So then we divide it by h. And as you may notice, when we expand this out, we actually get a very satisfying answer. Expanding that out, we get x squared plus 2xh plus h squared minus x squared over h. Now we just cancel out the x squareds. We're left with limit as h approaches 0 of 2xh plus h squared over h. Now these cancel out, and then h squared divided by h is just h, right? So then we're left with limit as h approaches 0 of 2x plus h. Now h is approaching 0, so h goes to 0. And then we're just left with 2x. So we found that the derivative of x squared, aka the slope of x squared, is 2x. Thank you guys for watching. I hope you learned something very valuable from this, and see you next time.